In this lecture, we're going to perform a mass balance on a reactor that has a single reaction. In this particular problem, ethylene, which we're going to represent with the letter E and has the chemical formula C2H4, reacts with hydrogen bromide, which we'll represent with the letters HB and has the chemical formula HBr. These two reactants form ethyl bromide, which we'll use EB to represent and has a chemical formula C2H5Br. This reaction is carried out in a continuous reactor. The product contains 51.7% ethyl bromide, EB, and 17.3% HBr. These are on a molar basis. The feed contains only ethylene and hydrogen bromide. We ultimately want to answer are the two questions at the very bottom of the slide. What is a limiting reactant, and what is the fractional conversion of this limiting reactant? And then what is the percent excess of the other reactant? To answer these questions, we're going to start by writing the chemical reaction and balancing it, and then drawing a process flow diagram, assuming a feed flow rate of 165 moles per second. Next, we'll do a degree of freedom analysis for our process flow diagram. We'll find the problem solvable. Next, we're going to write molecular balances, the mass balances that allow for us to solve for the unknown compositions and flows. And then we're going to, in the course of this, determine the extent of reaction and answer the question, what are the units of it? Something that we have not spent a lot of time on thus far. So before moving to the next slide, I would ask that you pause this presentation and do two things. One is to write and balance the chemical reaction between ethylene and hydrogen bromide to form ethyl bromide. Then also draw a process flow diagram with the information that you're given here and a feed flow rate of 165 moles per second. So please take a couple moments now, pause this presentation, and do that. Well, I hope you took a moment and attempted to write the chemical reaction and balance it, as well as draw the process flow diagram. What you should have obtained is shown here. First, the reaction of ethylene with hydrogen bromide to form ethyl bromide is shown here. The reaction is properly balanced. The stoichiometric coefficient for ethylene is 1, that for hydrogen bromide is 1, and that for the ethyl bromide is 1. This reaction differs from the equilibrium reactions we've considered up to this time in that 2 moles react to form 1 mole. And so there will be a change in the total number of moles between the inlet to the reactor and the outlet. For this problem, we have a single process, a reactor, in which we have a continuous flow coming in of 165 moles per second. The units are not shown here. But we don't know the composition of the stream coming in. So represent the mole fraction of the ethylene as y sub 1. The mole fraction of the hydrogen bromide is going to be 1 minus y sub 1 because we're told that there is no ethyl bromide in this feed to the reactor. The product composition we're given that the ethylene composition is 0.31 or mole fraction. The hydrogen bromide mole fraction is 0.173, and finally the ethyl bromide mole fraction is 0.517. So we form a significant amount of the ethyl bromide in this reactor. We don't know the molar flow rate of the product coming out. That's something we'll determine by writing mass balances. Next, in order to answer the questions that were posed in the original problem statement, we're going to perform a degree of freedom analysis, assuming that we're doing balances on molecular species. What we'll be doing is a balance for the ethylene, a balance for the hydrogen bromide, and then a balance for the ethyl bromide. In order to determine if the problem is solvable based upon our degree of freedom analysis, we have to first of all count the number of unknowns in the process flow diagram, count the number of independent reactions, count the number of independent reactive species, count the number of inert species, and then finally count the number of other equations that we might have. Then we're going to sum these all up. The first two, the number of unknowns and the number of independent reactions, will be given positive signs. Those will be things we add together. And then we'll subtract off the next 3 items from that to see if there are any degrees of freedom left. I would take a moment now and try to fill in this table and see if you can show that there are no degrees of freedom, that when we sum up the unknowns and reactions and subtract off the reactive species, the inert species, and other equations, that we end up with a sum of 0. I want you to take a moment now, pause the presentation, and try to do this on your own. Well, hopefully took the time in order to complete the degree of freedom analysis before moving to the slide. You should have found the results that are presented here. First, let's talk about the unknowns. There's two streams that enter or leave this reactor. The inlet stream to the reactor has a known flow rate, and the compositions information that we need has only one unknown associated with it. That's y sub 1. Y sub 1 is listed over here in the list of unknowns. If we look at the outlet from the reactor, the flow rate is unknown, n sub 1, and that's been added to the list of unknowns over here. The composition of the stream is completely known. We know values for all of the mole fractions of the species. So the total number of unknowns is 2. Next, we'll count the number of independent reactions. When there's only one reaction, the number is 1. If we had 2 or more, we'd have to determine if we'd have to have 3 or more. If we had 3 or more, we'd have to determine if all 3 are independent. So we'll have 1 in terms of the number of independent reactions in our table. Next, we'll count the reactive species. If we look at the chemical reaction that we have balanced, we find that ethylene is 1, hydrogen bromide is a second, and ethyl bromide is a third. So we have 3 reactive species. In this particular case, all 3 are independent. They're not present in the same ratio throughout the process. Finally, we'll look at the number of inert species that are present. We'll count those. There are none, so we'll have a value 0 in the table. And we're not provided any other equations, so we'll have a value 0 here in the table. To perform the degree of freedom analysis, we simply take the number of unknowns and add the number of independent reactions, and then subtract off the reactive species, the inert species, and any other equations. Doing that, we find that that sum is 0, so the problem is solvable. In order to write mass balances for this reactor, we're going to be able to write an expression for the generation minus consumption term in our mass balance equation. Remember, the mass balance equation is of the form 0 is equal to what comes in minus what goes out, plus the generation of that species minus the consumption of that species. So now we're going to focus in just on the G minus C part of that mass balance equation. We can write G minus C in terms of the extended reaction Xi from the definition of Xi, which is shown here. We know the number of moles that leave the reactor minus the number of moles that enter. N sub I is the moles that leave, N sub I 0 is the moles that enter. It's going to be equal to the generation minus consumption within that reactor of each species. And it's given by definition by plus or minus times the stoichiometric coefficient for that species in the balanced chemical reaction times the extended reaction Xi. We'll use a plus if the species is a product, and we'll use a minus if the species is a reactant. Take a moment now and see if you can write what the generation minus consumption term will be for ethylene, hydrogen bromide, and ethyl bromide, given this definition here. I would pause the lecture now and attempt to write out those expressions, and then when you're done, move forward to restart the presentation, the lecture, and see if you got the right answer. Well, hopefully you did pause and attempt to write this out. In this case, this calculation or this use of this expression is fairly simple, and we're going to review it. First of all, for the ethylene, if we look at the balanced chemical reaction, is one of the reactants, and its stoichiometric coefficient is 1. Since it's a reactant, we'll put a minus. We'll then introduce the stoichiometric coefficient 1, so we have a minus 1 times Xi. This is a generation minus consumption term for ethylene. For hydrogen bromide, if we look over here at the balanced chemical reaction, it 2 is a reactant, and its stoichiometric coefficient also is 1. So we'll have exactly the same expression for the generation minus consumption term for hydrogen bromide as we do for the ethylene. We'll have a minus because it's a reactant. We'll have a 1 here, which is hidden, but is there because its stoichiometric coefficient is 1, and then we'll have Xi, the extent of reaction. Finally, ethyl bromide's a product, so we'll have a plus. The stoichiometric coefficient for ethyl bromide is 1, and then we'll multiply by the extent of reaction Xi. Next, we're going to put these expressions into a mass balance for each of these reactive species. The mass balances, as we've discussed, is already of the form, will be of the form that 0, because we have a steady state process. Remember that here we had an accumulation term for unsteady state processes, but for steady state processes, we're going to assume that this term is 0, so that or by definition it's 0. So 0 is going to be equal to what comes in minus what comes out plus G minus C. And we've written down expressions for G minus C for each of these species in terms of the extended reaction. So given what you have thus far, you can actually go back in the presentation if you want to look at the previous slides, but I'd like for you to write out the mass balances for each of these species for this particular reactor. I would pause the presentation and do this before moving forward. Once again, I hope you did pause, and this is what you should have found when you wrote out the mass balances for each species. And we're going to go through each of these in some detail here. First, let's look at the ethylene balance. We're going to start off by saying 0 is equal to what comes in. So what comes in we obtain by looking over here at the stream, the inlet stream. We'll take the fraction of that stream from below the arrow, which is Y1, times the amount above, which is 165. So we have Y1 times 165 is what comes in. Next, we're going to subtract what comes out. If we look at the stream that comes out, the outlet, we see that we'll take the fraction of the stream, that is ethylene, which is 0.31, and multiply that by the amount above the arrow, which is N1. So we'll subtract off 0.31 times N1. And then from the previous slide, or one of the previous slides, we know that the generation minus consumption term for ethylene is a minus psi. And we're going to repeat this now for hydrogen bromide. Once again, 0 will be equal to the amount that comes in. The fraction of the stream that is hydrogen bromide is 1 minus Y1. We'll multiply that by the total amount above the arrow, 165. 1 minus 1 times 165 is the amount that comes in. We'll subtract off the amount that comes out, which is the fraction of the outlet stream, 0.173 that we obtained from below the arrow, times the amount above the arrow, N1. So we have 0.173 times N1. That's the amount coming out. Subtract that from what comes in, and then we'll add in the generation minus consumption, and that term here will be a minus psi from the previous slide. Last, we'll look at the ethyl bromide. The ethyl bromide, we're going to say 0 is equal to what comes in. There's no ethyl bromide in the inlet. We'll subtract off what comes out. Once again, it's the fraction from below, which is 0.517 times the amount above, which is N1. So I have 0 minus 0.517 times N1. And then we'll add the generation minus consumption term, which from the previous slide we know is a plus psi. We now have the three balances that we can write for this reactor. And we're going to have to try to solve these for the unknowns that we have here. We have three unknowns, Y1, N1, and Xi. And looking at these three equations, we can't solve for just one of the unknowns. Unfortunately, there's two unknowns in this last balance for ethyl bromide, and all three are in the first two balances for the ethylene and the hydrogen bromide. So let's get a little creative about how we do the algebra to solve for these three unknowns. And I'm going to lead you through that. We're going to start by adding the ethylene and the hydrogen bromide balances. We're going to take this equation for the ethylene balance and add it to the equation for the hydrogen bromide balance. If you look at this, by doing that, we have Y1 times 165 in this equation, and we have a minus Y1 times 165. So the Y1 times 165 will cancel in each of these two equations. And by summing these together, we'll end up with one equation in terms of N1 and Xi, which will combine with this equation from the ethyl bromide balance, which is another equation in N1 and Xi, to solve for those two unknowns, N1 and Xi. So let's start in on that. The very first thing we're going to do is add the ethylene and the hydrogen bromide balances. So those mass balances are rewritten here. All three of them are rewritten here. And I'm just going to add these top two together. The result you get is shown here. And we'll start over here on the far right and doing this addition. We have a minus psi from the ethylene balance and a minus psi from the hydrogen bromide balance. If I add this to this, I get a minus 2 psi. Next, let's add the term that involves N1. We have a minus 0.31 times N1, and we're going to subtract 0.173 times N1. So if we can add these two together, we have 0.31 plus 0.173. That gives us the 0.483 times N1. And there's a minus sign here because there's a minus in front of both those numbers. Finally, if I add this to this, The y1 times 165 cancels with this y1 times 165 and leaves us just with 165. That's where this number comes from. Okay, so what we're going to do next is add in this ethylene balance, right, with this sum of the two other balances, and see if we can solve those two equations together. So the ethyl bromide balance has been written down here in a way that will facilitate trying to solve these two equations simultaneously. And what we're going to do is we're going to multiply the second equation, the ethyl bromide balance, by 2, and then add it to the top equation, to the first equation here, which we obtain by adding the E and the HB balances. If we multiply this bottom equation by 2 and add it, you'll see that the term involving xi will drop out. That will give us an equation in terms of N1 that we can solve. Let's do that. The second equation has been multiplied by 2 here. We have plus 2 times xi. And we multiply this term by 2. We end up with minus 1.034 times N1. Adding these two equations together, a minus 2 xi cancels with a plus 2 xi. We add these two terms together, we end up with a minus 1.517 times N1. And that is subtracted from 165. That whole term is set equal to 0. We can rearrange this to solve for N1 pretty easily. N1 is 165 divided by 1.517, which is 109. So we're well on our way to solving for the unknowns here. Now that we have N1, we can plug it back into either of these two equations here to calculate xi. We can plug it in. The easiest one might be this bottom one here, since we only have 2 terms in it as opposed to 3 in the other. So we know N1's 109. Let's take, we have the EB balance, and what we're going to do is we're going to solve for xi from that. From the EB balance, we see that xi is equal to 0.517 times N1. We just multiply those two numbers together, we end up with 56.2. And then from the ethylene balance, we're going to solve for y1. Y1 is, if you rearrange this equation up here, is 0.31 times N1 plus xi divided by 165. And we end up then with a value of 0.545. Now the extended reaction is going to have the same units as the other terms in this mass balance that we have here. The units of these terms, of the flow rate in and the flow rates in, the flow rate out, are both moles per second. So the units of xi also have to be moles per second. We're finally to the point that we can actually answer the questions that were posed initially in the problem statement. First, what is a limiting reactant? And then what's a conversion of that limiting reactant? What's the percent excess of the other reactant? To determine limiting reactant, we need to know the flow rate of ethylene and hydrogen bromide, the two reactants that come in. We can calculate these flow rates by taking the total flow, total inlet flow to the reactor, which is 165, and then multiplying by the fraction of that, which is ethylene, 0.545. So the ethylene flow coming in is 90. Likewise, the hydrogen bromide flow is going to be given by the total amount coming in, 165, times a fraction of that stream, which is hydrogen bromide, 0.455. That gives us 75. If we compare the ratio of the ethylene flow to the hydrogen bromide flow to the stoichiometric coefficients of those species, the ratio of the stoichiometric coefficients for those species, and from the balanced chemical reaction, we can determine which is the limiting reactant. The ratio of flows for ethylene to hydrogen bromide coming in is 90 to 75. The ratio of the stoichiometric coefficients is 1. Stoichiometric coefficient for ethylene is 1. The stoichiometric coefficient for hydrogen bromide is 1, so this ratio is 1. I think it's pretty clear that 90 is greater than 75, so this ratio is greater than 1. And since this ratio is greater than 1, which is the ratio of the stoichiometric coefficients, ethylene's in excess, and hydrogen bromide is limiting. So now we know hydrogen bromide is limiting. How much of this reacts? What is the fractional conversion of the hydrogen bromide? To determine that, we need to know the amount of hydrogen bromide that reacts, and then we'll divide that by the amount that enters. The amount of hydrogen bromide that reacts is equal to the amount that enters minus the amount that leaves the reactor. The amount that leaves the reactor is the flow rate of the outlet stream times a fraction of that stream, which is hydrogen bromide. The flow rate we've determined is 109. The fraction of this stream, which is hydrogen bromide, is 0.173. So take this difference to determine the amount that reacted in the reactor, and then divide it by the amount that was fed to get the fractional conversion. you should find it's 0.749. We know the ethylene's in excess. To determine the percent excess, we'll take the amount of ethylene that was fed, which is 90, and subtract off the amount of ethylene that would react stoichiometrically with all the limiting reactant, with all the hydrogen bromide. And divide that by the amount of ethylene that would react stoichiometrically with the limiting reactant, the hydrogen bromide. These two numbers are the same. If the flow rate of hydrogen bromide coming in is 75, then the amount of ethylene that would be needed to stoichiometrically react with all this would be 75 as well. We need 1 mole of ethylene bromide for every mole of hydrogen bromide. So if we have 75 moles of hydrogen bromide, we need 75 moles of ethylene. So to determine the percent excess, we'll take the amount of ethylene that was fed, subtract off the amount that would be needed to react stoichiometrically with all the HB at 75, and then divide that by the amount that would be needed to react stoichiometrically with all of the HB. So if you do this and multiply by 100 to convert the fraction to a percent, you find it's almost 20%, 19.9%. This is a problem we'll work in class. It's a homework problem, and once you complete it in class, you'll be ready to turn it in. It follows in a very similar manner to the work that we did in this lecture.